Hello. As part of getting ready to do our stereo, we're going to need to find some long straight lines to do our matching. Those are the primitives that we're looking for here. So what we're going to look at in this set of slides and a little bit of video is about how to take those edges that we found in the previous set of videos and find some long straight lines. And the technique that we're going to use is called the RANSAC technique. RANSAC is sort of an acronym based on the word random sample and consensus. The idea that you take a couple of features from the image, you estimate a model, and then you look to see how well that feature fits the rest of the data in the image. And we're going to apply this to finding the straight lines. So the RANSAC is not just about finding straight lines, it's a model-based technique. So we can use other kinds of models. You could find circles, you could find ellipses, you could even find more general shapes. But we're just going to use it to find some straight lines right here. One of the great things about it is that it can even work in a very cluttered image, which is the case that we have right here. We do have a fair amount of straight lines, but as you saw from the edge detection results that we saw last time, there are an awful lot of edges in there, and we want to be able to find our straight lines even in the midst of all that other stuff. Another interesting feature about this algorithm is it's what you might call an anytime type algorithm, or it's in that sort of family. It's not guaranteed to always work, but you can also, by the same token, you can determine how often it fails, or the worst kind of performance rate on failure. So you can pick that failure rate, and from that, then you can determine how long the algorithm works. The core of the algorithm is based on this finding a model feature, and we're assuming that the model feature in this case is going to be defined by some edge points. And in this case, we're just going to assume that we need to have t of those edge points. Now, of course, if we're finding straight lines, we all know that 2 points are enough to find a straight line. But if you're fitting a circle or something, then you would need 3, and so on. We're also going to assume another parameter, and that's this parameter v, which says that if we hypothesize some sort of a structure like a line, as well as having the 2 points which initially define the line, we're also going to need to have a number of other points, other edge points in the image that help confirm that we actually have found a valid line and that it's not just a pair of coincidentally lined edge points. So those are our 2 parameters. The algorithm itself can be expressed very easily, and this is essentially the whole algorithm, at least in core right here. We iterate over a number of trials, and if we don't succeed in finding the feature that we're looking for in those trials, we fail. So that's the first bit. This trials parameter that we've got right here, we'll look and see how we can estimate that parameter in a minute. The first step is we select our 2 feature points randomly, and then we test to see whether it's good. So in this case, we find our straight line. We find the line through those 2 randomly chosen points, and then we check to see how many other edge points lie close to that straight line or whatever the feature we have. And if we get more than the v of them that we need, then we say we've got a success. So that's the whole algorithm. It's easy to implement just in a few lines. I mentioned about this termination limit, and that's a little bit of an interesting question about how you can relate the probability of failure to that number of trials that we make, that's in the loop. And it's pretty straightforward. We need to have a little bit of data about our problem, and we'll see how we do that. So the core of it is we start with a probability of the algorithm failing to detect the feature. So you can say it's you're going to have a 1% failure rate, or 1/10 or 100% failure rate. That's up to you to pick. Then you have to go look at your data set. And from that data set, we're going to estimate 2 probabilities that come from the data. The first is this P1, which is the probability that some data point belongs to one of the features. So we saw our edge sample set. There were a lot of real edges, but there were also a lot of just random edges from other objects, not on the blocks that we're looking for. So this is the probability that one of those edges lies on one of those blocks. The second probability is the probability that if you find the first point on an edge, what's the probability that the second point is on the same feature? So that would be a smaller probability. So you've got a point on the first point that's on the edge. What's the probability that you've got one of the other edge points? Because you want a straight line that goes through those particular set of points. Okay, so we have to estimate that from the data, and you can do that offline in advance from some of the sample images. Okay, but that's all we need to be able to estimate the number of trials that we need in order to get the algorithm to sort of properly achieve this failure rate. So let's do a little bit of probability. We fail overall if we fail on every single one of the trials. So if this is the probability of failing on one of the trials, then we have to fail on this many consecutive trials. So that's straightforward. Well, what's the probability that we fail on one trial? Well, probability of failure on one trial is 1 minus the probability of succeeding on one trial. And we succeed on one trial if we pick the first point that's on a good feature, and we pick all the remaining t minus 1 points also on that same feature. So that's the probability of succeeding. Okay, so we've got all the pieces we need in terms of the terms that we've defined up here. We plug them all into the formula, we rearrange the terms, and we solve for the number of trials, and there's our formula right there, nice and straightforward. Well, let's apply that to our real data set. Okay, so in this case we're looking at model lines. We need 2 points, and we're going to say that we accept a point that if there's sort of 28 neighboring points within 2.5 pixels of a line, that's what we need to kind of get initially a valid line as far as RANSAC is concerned. We're also going to have a kind of verification threshold later that says that we need at least 130 points on that line. And so we're going to use that for later. Here's our probabilities. Here's our failure rate. Here's our probability on the first feature. Here's the probability on the second features. You plug that into the formula, and we get 688 as the number of trials before the algorithm terminates and doesn't give you any more. And in this particular case, we're not interested in just one line. We're interested in all lines. And so therefore, after we found one line, we extract the data points that are associated with that line, and then we run the algorithm again. And we keep doing this until eventually the algorithm fails, and that's where it says that it's found all the lines that it can from that data set. Unfortunately, I remember our image was so cluttered with all the edge points everywhere, and actually we find quite a lot of lines, 203 on the left, 216 on the right. But it did a good job of finding lines, and if we look in the image carefully, we see that we found the lines that we want to lie on the object. But in order to make the remaining portions of the stereo matching and all a little bit easier, what I'm going to do is I'm going to blank out, I'm going to sort of mask away the center portion of the image, okay, which is where a lot of the complexity comes from. And once we do that again and run our edge detector again, we get a smaller subset of lines, 96 and 108. If we sort of zoom in, as we will in a minute, we'll see actually that we do get the lines that sort of lie along the edges of the wedges that we're looking for here. Now, one of the problems that we have, or one of the things that we haven't done yet, is finding the actual extent of the segments, because we're going to use that for the stereo matching. At the moment, because we've just picked up the 2 points on the line to estimate the equation of the line, that just gives us an infinite line which goes through the points. So as you can see with these little bit of the wedge right here, it sort of starts there and ends there, but the line itself goes all the way across the image, and we don't really want that. So one of the